Hello and welcome you all. Dear students, this is the quick revision session for fiber optic cables used for telecommunication. So let us discuss the basic block diagram of the optical fiber communication system. Before that, we'll discuss the structure of fiber optic cable. So this is the basic structure of fiber optic cable. There are three major layers. The innermost layer, this layer is called core layer. It is made from glass or plastic. We know that in case of optical cable, the signal is in the form of light rays. So this is the core layer. Inside this core layer, the light rays are traveling by causing total internal reflection. This layer is surrounded by one more layer that is called cladding layer. The refractive index of cladding is made less than that of core layer. When the optical cables are used in bundles, it may happen that some of the light rays may get escape from the core layer, enters into the cladding layer. Function of cladding layer is again redirect those light rays to the core layer. The last layer is the protecting layer, which is called a jacket layer. Now, this is the generalized block diagram of optical communication system. At the input side, we are using the source. This source may be a certain electrical quantity that we want to transmit through the fiber optic cable, or it may contain certain physical data. It can be speech signal or image, or it may be video signal and so on. We are using analog or digital interface. As the name indicates, the signal may be analog or digital. So we want to interface it to the system. So corresponding block is used. Then through the fiber optic cable, the only light rays are allowed to transmit. So we have to convert this electrical signal into the light rays. For that, optical source is used. The optical source may be LED, that is light emitting diode, or it may be a laser, especially injected laser and so on. The output of voltage to current converter, which is by default a current, is applied to the optical source. The output of optical source is photons or light rays. These light rays are driven by the current which is produced by this block. So you can well say like this signal, light rays or photons are modulated by the source signal. Then at the input side of this is the fiber optic cable. At the input of fiber optic cable, at the source end, we have to use one coupler. Coupler is a device, as the name indicates, which couples this optical source to the fiber optic cable. So this is the function of the coupler, which is used to couple. For example, if you are using LED, it couples light of the LED to the optical cable. This red portion shows fiber optic cable. Then signal regenerator block. When the signal is transmitted, then depending on the transmission length and depending on other parameters, the attenuation of signal may take place. This attenuation may be due to the absorption of the light rays or may be due to the scattering of light rays. This is happening because of the properties or characteristics of the material used to manufacture the fiber optic cable, as well as there may be dispersion of light rays. So in short, you may say like this: the signal is getting attenuated or signal wave shape is getting disturbed. So to regenerate the signal, this signal regeneration block is used. Typically, this signal regeneration blocks is erbium doped optical amplifier. So function of this optical amplifier is to accept the incoming signal from through the fiber optic cable and regenerate it, recover the wave shape of the signal, and recover the attenuation, and then again retransmit the signal. At this end, so this particular portion up to this coupler and fiber optic cable is the part of transmitter. Then at the receiver side, this portion is related to the receiver part. At the receiver side, again we are supposed to make use of the coupler. The function of this coupler is, see, at the receiver we want to recover the electrical signal, because through the fiber optic cable light rays are transmitted. Original signal was not light ray. We have to convert these light rays into electrical signal. For this, optical detectors are used. A variety of optical detectors are available. Pin photodiode may be used, that is p-type, then intrinsic type, n-type device or avalanche photodetector may be used, or photo transistors can be used. So To couple this optical detector to the fiber optic cable, this coupler is used. Then at the transmitter side, we have converted voltage to current. So at the receiver, again we have to convert this current into the voltage form. Then analog or digital interface and final block, and finally the signal is available at the destination, which is in the same form as that of the original signal transmitted by the source. This is the graph of attenuation, that is TL. TL stands for transmission loss, which is measured in decibels per kilometer, versus wavelength. Lambda is the wavelength, it is in nanometers. So this is the graph of attenuation of a signal when the data is transmitting through the fiber optic cable versus the wavelength lambda, versus operating wavelength lambda. Different windows are shown. So these are called transmitting windows. First window is around 800 to 900 nanometer. Second window is centered at 1300 nanometer. The third window is centered at 1500 nanometer. Now let us discuss few important terms. First is critical angle. Critical angle is denoted by phi c. Consider the situation where we are considering two dielectric medium, I mean rather the interface of two dielectric medium. Say dielectric medium 1 having refractive index N1, another dielectric having refractive index N2. Why to consider two different dielectric medium? Reason is we are talking about fiber optic cable. Inside the fiber optic cable, the material is glass or plastic. Outside, it is usually a free space. So whenever there is a change in refractive index of the medium, we need to talk about reflection or refraction of the light ray. So first term related to this is critical angle phi c. I have shown three different diagrams. This is the incident ray, which makes an angle phi 1. At one particular value of phi 1, you are getting a refraction. So this is the refracted ray, which makes an angle phi 2. As you go on increasing this incident angle of incidence, then at one particular stage, value of phi 2, that is value of angle of refraction, becomes 90 degree. This is the limiting angle, which is called critical angle. Now, as you again go on increasing this value, then you will get the reflected ray. Instead of refraction, you will start getting the reflection. This particular condition or this particular value is called critical angle. So the angle after which you will start getting the reflection is the critical angle. Definition is maximum possible angle of incidence at which if the incident light ray is incident at an intersection of two dielectric medium. As I said, this is the boundary between two dielectric medium N1 and N2. Then it gets refracted at an angle 90 degree. So this is about the definition of critical angle. Another term related to this is acceptance angle. We know that inside the fiber optic cable there should be reflection and not the refraction. Consider a particular code. Let us say we are talking about this light ray X. This light ray X is such that it makes an angle theta A, which follows the condition of critical angle. So it causes internal reflection inside the optical cable. It is also called, denoted by TIR, that is total internal reflection. So this light ray X makes an angle theta A and it causes total internal reflection. This is the required phenomena in case of optical cable. Consider another light ray Y. It is not in this acceptance code. So this light ray enters into the core layer, but it will not cause internal reflection. It will enter into the cladding layer. This is the cladding layer. It enters into the cladding layer and eventually this light ray will lost. So this is of no use. So what we want to that light ray should cause total internal reflections inside the optical cable. So theta A is the limiting angle. Any angle greater than theta A will not cause internal reflection. So acceptance angle is the maximum angle at which light enters the fiber and causes internal reflection. Next term related to this is NA, that is numerical aperture. The sign of maximum angle is theta A. An incident ray makes with core axis. This particular dotted line indicates core axis and travels through the core using TIR, that is total internal reflection, is called numerical aperture. Now as far as the numericals are concerned, you need to remember this list of formulae. So first is critical angle phi c. which is sine inverse of n2 by n1. Second is numerical aperture, square root of n1 square minus n2 square. n1 and n2 are refractive index of two medium. Delta, that is relative refractive index difference of the two refractive indices, is n1 minus n2 upon n1. Numerical aperture Na is n1 square root of 2 delta. If angle is small, then that is related to solid state angle. It is denoted by zeta. This notation is zeta, which is given by pi Na square. Next part is the condition for guided mode and V number. You may expect the question like this: explain the condition of guided mode and define V number of an optical cable. What is the meaning of guided modes? Through the core layer, there should be total internal reflection of the light rays. So all such modes, all such light rays which are causing total internal reflection throughout the core layer are called guided modes. So corresponding condition is N2K less than beta less than N1K. N1 is refractive index of core, N2 is refractive index of cladding, beta is the phase shift, and K is the constant which is given by 2 pi by lambda, where lambda is the wavelength. There are three conditions related to this equation. If N2K is less than N1K, it represents guided mode. Conditions for guided mode. That means if this condition is satisfied, all the light rays, all the modes which are entering into the core layer will be guided by the optical cable. Second condition, if N2K is equals to beta, requirement is N2K should be less than beta. If it is equals to beta, it gives cutoff condition, there won't be any propagation. If beta is less than N2K, then it indicates leaky mode. That means there is a power leakage from core layer to the cladding layer. Then V number. This is a particular number which decides the total number of propagating modes inside the fiber optic cable. This number also gives an idea or gives the value of a point after which the cutoff condition starts. These are the mathematical equations of the V number. First is V is 2 pi by lambda. A is the radius of core layer. Na is the numerical aperture of the optical cable. Another formula is V is 2 pi by lambda. A N1. N1 is refractive index of core, square root of 2 delta. Delta is the relative refractive index difference between core and cladding. Now let us discuss the classification of optical cable. So broadly, first type is based on operating modes. There are two operating modes. First is single mode. As shown in this diagram, S stands for source, D stands for detector. This middle portion is the part of optical cable. As shown in this diagram, only a single light ray is traveling from source to detector. So it is a single mode cable in which attenuation and micro bending losses are minimum. If multiple modes, multiple wavelengths are transmitting through the optical cable at the same time, then it is called multimode fiber optic cable. In this case, there will be more dispersion losses because many wavelengths, many modes are transmitting simultaneously and they will not appear at the output at the same time. Next classification is based on refractive index profile. We know that the two major layers of the optical cable is the innermost layer, that is the core layer, and second is the cladding layer. So refractive index of core is N1, that of cladding is N2. This portion is called core layer, which I have drawn with the blue ink. This dotted line indicates axis of the core layer. Outer portion, cylindrical structure, is for the cladding layer. Refractive index of core is N1, that of cladding is N2. As we move from N1 to N2, there is a sudden change. Look at this change. There is a step change. So it is called step index fiber. Due to sudden change in the refractive index, as we move from core to cladding, there will be more dispersion losses. Another is the graded index fiber. Look at this refractive index. So this dotted line indicates axis of the core layer. Refractive index of core is N1, that of cladding is N2. As we move from core to cladding, there is a smooth variation in the refractive index. That is not a sudden change. Such type of waves, these modes are shown by this sinusoidal type of waveforms. This is the type of waveforms which we are getting in case of such fiber optic cable, which are called graded index fiber optic cable. This gives the greater bandwidth compared to single step index fiber optic cable. Next part is the comparison between single mode. It is also called SMSI, single mode step index fiber, and multi-mode, that is MMSI, multi-mode step index fiber. Basically, as the name indicates, in case of SMSI, only a single wavelength, single mode is traveling, whereas multiple modes, multiple light rays are transmitting simultaneously in case of multimode fibers, that is MMSI. So comparison says first point is only one mode propagates, that is a single wave propagates. In case of MMSI, multiple mode propagates. Core diameter is small, so it is difficult to launch the optical cable. I mean, to launch the optical power inside the cable. In this case, core diameter is large, so comparatively it's easy to launch optical power inside the cable. There is no intermodal dispersion. In this case, intermodal dispersion occurs because more wavelengths are used, that is, more modes are existing. The duration of output and input pulse is same, that means width of both output and input pulse is same. Whereas in this case, in case of MMSI, the broadening of output pulse takes place because many modes, many wavelengths are used which are traveling simultaneously, which follows different paths, and they are not reaching the output at the same time. So spreading of output pulse takes place. LED cannot be used as a source. In this case, LED can be used as a source. This gives higher bandwidth. MMSI gives lower bandwidth. V number is less than 1.5. In this case, it is greater than 1.5. It is used for long distance communication. It is mainly used for short distance communication. Applications includes television broadcasting, then long distance telephony system, whereas applications of MMSI includes land system or video surveillance. Now the numericals of this part is pretty simple. I have made a list of formulae. If you know this formulae, you will be in a position to attempt any numerical. First, let me explain this list of formulae. N is numerical aperture, which is square root of n1 square minus n2 square. N1 is refractive index of core, n2 is refractive index of cladding layer. Or it is also given as n1 square root of 2 delta. This value delta is called relative refractive index difference between core and cladding. It is given by n1 minus n2 upon n1, formula number 7. Then V number, that is also called normalized frequency. The formula is 2 pi by lambda A into NA, or I have simply put this value of NA over here. So formula can be 2 pi by lambda A. NA means N1 square root of 2 delta. Then acceptance angle theta is sine inverse of NA. Zeta, that is solid state acceptance angle, pi NA square. Number of modes that are propagating through the fiber. If it is step index fiber, formula is V square by 2. For gradient index fiber, number of modes, which is denoted by mg, is V square by 4. This formula we already discussed. Delta, relative refractive index difference between core and cladding, is n1 minus n2 upon n1, and critical angle, that is phi c, is sine inverse of n2 upon n1. Now let us discuss one numerical. If a multimode step index fiber has core refractive index 1.5, so core refractive index means n1 is 1.5, cladding refractive index, that is n2 1.38, core radius 25 micrometer. Core radius is denoted by small a, so small a is 25 micrometer. Since given value is in micrometers, we need to convert it into meters, so it is 25 into 10 raised to minus 6. Then operates at a wavelength 1300 nanometer. Wavelength is denoted by lambda. It is 1300 nanometer. Again, we need to convert it in terms of meters. So it is 1300 into 10 raised to minus 9. Now, as I said, everything is formula based. You just have to put the values. So first part, do the calculation of numerical aperture. Look at the given values. I can simply make use of first formula, NA square root of n1 square minus n2 square. So put the values, answer is 0.5878. Then second part, normalized frequency, that is V number. I have first formula 2 pi by lambda A NA. So it is 2 pi by value of lambda A, that is 25 micrometer, that means 25 into 10 raised to minus 6 into NA. Value of NA we have calculated in the first part. So answer of V number is 71.024. Third part, acceptance angle theta A sine inverse of Na. So simply you have to take sine inverse of value of Na, that is 0.5878. This is 36 degrees. Zeta, fourth part, solid acceptance angle, that is zeta. We have formula pi Na square. So this value is 1.08 radians. Do remember this value theta A is in degrees, whereas zeta I have calculated in radians. Since it is given fiber is multimode step index fiber, for SIF step index fiber, number of modes are v square by 2. So number of modes are 71.024 brackets square upon 2. So answer is 2.22.2. This is the value which represents total number of modes that are propagating through the fiber. So it must be integer. So approximate value is 2523. Now let us discuss different losses taking place in an optical cable. So there are different types of losses. First is absorption, second scattering, third attenuation, fourth bending losses, and fifth is coupling losses. You may expect the direct question like explain the absorption, scattering, and attenuation in case of optical cable. So first is absorption losses. As the name indicates, the material which is used to manufacture the optical cable can cause absorption of incoming light rays. It produces a heat which represents losses. Again, there are different subcategories. First is intrinsic absorption loss. This is due to the basic atoms that are used in case of optical cable. Next is extrinsic atoms. While manufacturing the optical cable, some impurities are added. Again, it causes absorption of incoming light. And third is atomic defects. There may be some atomic defects in case of the material which is used to manufacture the optical cable, which again causes absorption losses. Next is the scattering losses. Scattering means the deviation or change in the direction of light ray. So this change is due to the non-uniformities present in the material of the optical cable. This causes power losses. That means if I'm talking about a multimode fiber, then power from one mode may get transferred to the other mode, which represents the losses. Again, due to the imperfections in the material, scattering of the light rays takes place. All this represents the type of loss, which is the scattering loss. For multimode fibers, since there are many modes and there are different material decomposition, in that case, the scattering losses will be more. Third is the attenuation. In case of optical cable, attenuation represents reduction in the intensity of the light ray. This reduction is due to absorption and scattering, which represents attenuation loss or attenuation of optical cable. It is denoted by alpha, which is measured in dB. Mathematical equation is 10 by L. L is the length of optical cable. Log P in upon P out. P in is the input power that is applied to the at the input end of optical cable, and P out is the power coming out of the optical cable. Next is the bending losses. As the name indicates, if the fiber optic cable is bent sharply, then it may happen that angle of incidence is less than the critical angle, which will not allow the total internal reflection, and it produces errors, or it creates losses. Or if the fiber optic cable is bent sharply, then mechanical failure takes place, and because of which again losses takes place. Next is the coupling losses. See, at one end of the fiber optic cable we need to connect source, then at other end, at the receiver end, we need to connect detector. So to connect source and detector to the fiber, different techniques are used. So due to this coupling, losses are produced. Another thing is, if you want to join two fiber optic cables together, then again there are different techniques available, but while joining the two cables together, there can be misalignments of the core layer, and because of which again losses are taking place in the system. Part is the dispersion. This is basically the phenomena in which the width of the output pulse is increased. That means the spreading of optical pulse is called dispersion. This is because the different wavelengths, different modes which are traveling through the fiber optic cable follows different paths having different velocities, because of which the dispersion or spreading of the pulse takes place, which is referred as the dispersion. There are two major types. First is intramodal or chromatic dispersion. We are using light source at the input side. Every light source has limited spectral width or finite spectral width. The different light rays or different spectral components which are coming out from the light rays follow different propagation paths. So the propagation delay difference between different spectral components from the source causes spreading of the output pulse, which is called intramodal or chromatic dispersion. It is of two types. One is material dispersion, that means the material which is used to make the fiber optic cable itself is a dispersive nature which causes spreading of the output pulse, or waveguide dispersion. The fiber optic cable through which the light rays are traveling is called a waveguide because it is guiding the waves which are passing through it. So because of its structure, because of its nature, again spreading takes place, which is waveguide dispersion. Next is intermodal or modal dispersion. As shown in this diagram, if I'm talking about a multimode fiber, MMF, multimode fiber, in that case, different modes, different paths, different light rays are following different paths, having different velocities. So they will not reach the output at the same time, which causes spreading of the output pulse. It is referred as intermodal or modal dispersion. Dear students, that's it for the quick revision of this unit. So thank you. Thanks a lot for watching this video.